So in this section, we're just going to use the ideas we developed in the previous videos with intercepts and asymptotes. And we're going to use those to get a sketch of the rational function. Then we're going to look at our TI to confirm that it looks like what we got. So in the first one, I have this function, and they want us to find the vertical asymptote, horizontal x-intercept, and y-intercept. And we know what steps to go through to find those. So before I do anything, I'll go ahead and factor this, because we're going to need to factor it anyway. So there's my rational function. The VA are coming from the denominator being 0. So I'll just do that quickly. X is equal to 6 if you set this equal to 0, and x is equal to -1 if you set the other factor equal to 0. For the horizontal asymptote, remember, you compare the degrees, and in this case, the degree of the numerator, since this is just a constant, the degree of all constants is 0. And in the denominator, the degree is a squared, so that's a 2. And since the numerator is less than the denominator, the denominator wins, and we get y equals 0. So the denominator gets bigger and bigger, and 6 divided by bigger and bigger is going to go to 0. For the x-intercept, remember, we would set the numerator equal to 0. And in this case, if I set the numerator equal to 0, that gives me some nonsense. So there are no x-intercepts. For the y-intercept, remember, we let x be equal to 0. So I have y equals 6 over -6. If I put zeros in the x's, that's going to give me -1. So we do have a y-intercept of 0, -1. So let's put these guys together and get a sketch of the graph. All right, so I have a VA at x equals 6, another VA at x equals -1. And I also have a horizontal asymptote at 0, so the x-axis is essentially my horizontal asymptote. And I do have a point on my graph, which is 0, -1. That's the y-intercept. So if it has to go through this point and approach the asymptotes, I'm guessing this should go like that, and maybe something like this to approach the other asymptote. Now, how do I know that like something like this doesn't happen? How do I know that it doesn't cross the horizontal asymptote? Because we said it's possible to cross the horizontal asymptote, right? Or maybe it'll go something like this and approach the asymptote up there. So let's go check to make sure that the first one I had will work, just algebraically, analytically showing, because we could refer to our TI and get it, but how would we know algebraically? So here is my horizontal asymptote, and here is my function. If they are supposed to intersect and cross each other, they must be equal. S of x will be equal to 0 if the HA is crossed. Always, your function will be equal to the horizontal asymptote if they are supposed to intersect and cross each other. But if I take my function and I set it equal to my horizontal asymptote of 0, and then I multiply both sides by this guy, these cancel and I have 6 equals 0, which doesn't make sense. So if the HA is crossed, when you set the horizontal asymptote equal to your function, you will get solutions, and that's when the horizontal asymptote will be crossed. So in this case, it's not crossed, which means if I have this point, the y-intercept on my graph, since the horizontal asymptote is not crossed, that point has no choice but to approach this guy and approach that guy. It cannot go up and cross the horizontal asymptote. Now I only have to see what happens to the left of -1, what happens here, and to the right of 6, what happens here. And like before, we can quickly go put in a point and see what's going to happen. So on the left, if I put x equals -2 to the left of -1, and I go put it in my function, so I go put -2 in all the x's, I get x squared, which is -2 squared, -5 right here, times -2 is +10. I don't even care what that number is. I know it's going to be a positive value. So my graph at -2 gives me some positive value, which means it has to approach the asymptotes and look like that. And on the right, let's say I put x equals 7 into my function, and remember, this is my original function. So y is going to be 6 over 7 squared is 49, 5 times 7 is 35, minus 6, and it looks like that's going to be also a positive number. So I don't care, it's going to be somewhere up here. If it's going to be somewhere up there, or even smaller, if I actually go do the math, it's going to be 6 over 49 minus 41, I guess. 8, that's going to be small, a positive 3/4. So it's going to be somewhere here, and that means it has to approach that asymptote and that asymptote. So roughly speaking, that's what my graph looks like. Let's quickly go look at the TI as well. So I put the function 6 over the quantity x squared minus 5x minus 6 into my TI. Make sure you have parentheses around the denominator, and I'm going to do a zoom 6 on it. And it looks like it does look a lot like the one we sketched. The horizontal and vertical asymptotes are not too clear there, but we know they happen at -1 and +6. And also on the TI, it looks like you're touching the x-axis, but you're not, because that is a horizontal asymptote, and we showed that it does not get crossed. Now let's go look at the domain and the range. So for the domain, that's pretty easy. We know that x cannot be the -1 vertical asymptote and the 6 vertical asymptote. Let's put it in set notation, x such that those guys cannot equal to -1 and -6. And for the range, we'll say y such that everything gets covered except that horizontal line y equals 0, this guy that never gets crossed. Based on the work that we showed right here, it doesn't get crossed, so we'll say y such that y does not equal 0. All the other y's are good. Below the x-axis, I have a red graph. And above the x-axis, I have red graph happening. So exclude 0 from the range and exclude -1 and 6 from the domain, and you're good to go. Now let's talk about slant asymptotes. These guys occur when the degree of the numerator is greater than the denominator, but only by 1. So when the degree of the numerator is only 1 higher than the denominator, that's when you're going to get a slant asymptote. In other words, not a vertical line like the 6 and the -1 that we got in the previous example, but a line that's slanted. Scratch that, not in reference to the VA, I mean in reference to the horizontal asymptote. So just like the horizontal asymptote here is y equals 0, if the degree of the numerator and denominator are different by 1, the numerator being greater, then you're going to get a slant asymptote, and instead of a horizontal asymptote, you're going to have the graph approaching a linear function y equals mx plus b as you walk to the left or the right as x goes to positive or negative infinity. Here's what I mean. For example 2, notice the degree on top is 2 and the degree in the bottom is 1. Whenever the top is 1 greater than the bottom, you're going to have a slant asymptote as opposed to a horizontal asymptote. So the VA here we can quickly get from the denominator equal to 0, that's going to be 1. That's no change there, same as before. For the horizontal asymptote, we would say none originally when we would see that the degree of the numerator is greater than the denominator. But since 1 greater, we're going to say it has a slant asymptote. So again, you need that 1 bigger only. Bottom 2 or bottom 1, top 2. Or maybe you have an x to the 4th on top and an x cubed in the bottom. They're off by 1. The bottom always has to be higher by 1 for you to get a slant. Now, how do I find the slant asymptote? We already have the horizontal or the vertical asymptote for this one, so I could sketch that quickly. So we know x equals 1 is a VA. Now for the slant, which we know because the degree is 1 higher than the bottom, we're going to have to go do long division to get the slant asymptote. So I'm going to take x squared plus 2x, and I'm going to divide into it the denominator, x minus 1. The only guy that matters is this guy and this guy. So in order to get from x to x squared, I have to multiply it by x. So you basically say, what do I multiply what do I put on top so that when I multiply the top guy with this x on the left, I get this x squared that's underneath. So now once you have that there, then you just go on the side and basically multiply x and x minus 1, which gives you x squared minus x, and that goes underneath here, x squared minus x. So basically, I multiplied and distributed this into both of them. Immediately after that, you switch your signs, and when you do that, the first terms have to disappear and you get 3x. Now, to get from x, from up top, to 3x, or from, sorry, let me erase these. To get from x to 3x, you're going to have to multiply by a 3 to get from x to 3x. So I'm going to put a positive 3 up there to get my 3x, and I'm going to take that 3 and multiply it by x minus 1 and get 3x minus 3. So in other words, now you're multiplying 3 times x and 3 times negative 1, and that's going to give you 3x minus 3. And just like long division, you immediately switch your signs. The first guys have to cancel, and then you have a remainder of 3, and you don't continue any further because you don't have any x's left. The degree of your remainder is smaller than the degree of what you were dividing by. So in other words, x squared plus 2x over x minus 1 is equivalent to what you got as your quotient plus the remainder. So basically all I did was I did long division like you do with numbers, where you get an answer along with your remainder. Now this means as x goes to infinity, to plus and minus infinity, this piece dies out and goes to 0 because you have 3 divided by something big. So naturally that's going to die off. And this is the guy that takes over. So my slant asymptote is going to be that line y equals mx plus b, in this case y equals x plus 3 as my slant asymptote, which means if I were to graph my slant asymptote, it has a y-intercept of 3 and a slope of 1. So 1 up, 1 over, or 1 down, 1 to the left, 1 down, 1 to the left, 1 up, 1 to the right, and that is my slant asymptote, y equals x plus 3. So in this case, no horizontal asymptote, but a slanted line that your graph approaches. We can also go find the x and the y-intercepts quickly and then get a sketch of this graph. So for the x-intercept, we're going to make y0, and we said numerator essentially equal to 0. So if I set numerator equal to 0 from my original function, which is up here, I'm going to have x, I'm going to factor the numerator, plus 2x equals 0. GCF is x, x plus 2 equal to 0. So either x equals 0 or x equals negative 2 are my two x-intercepts. So 0, 0, and negative 2, 0. And then for my y-intercept, I'm going to make x equals 0. So that looks like it's just going to be y equals 0 over negative 1, which is 0. So I have these two dots on my graph. I have 0, 0, and I have negative 2, 0. So negative 2, 0 is here. So basically, if I have to go through those red dots and approach my asymptotes, then I'm guessing I'm going to do something like this to approach that slant asymptote, and this to approach that vertical asymptote. So I've taken care of to the left of my vertical asymptote of 1. Let's see what happens to the right of the vertical asymptote of 1. So I'm just going to pick like x equals 2, put it in my function. That's going to give me y equals 2 squared plus 2 times 2 over 2 minus 1. Again, I'm going here in my function to see what I get. That's going to be 4 plus 4, which is 8. 8 over 1 is just 8. So the ordered pair 2, 8 is somewhere up here, let's say, is on my graph. So it has to approach the vertical asymptote of 1 and also go approach the slant asymptote, which means if I have a dot here, it kind of has no choice but to go that way, approach that green asymptote, and go this way and approach the other green asymptote.